Hello, my name is Eric Turner, and I'll be discussing Lab 5, which covers Faraday's Law. Some of the goals of the lab were to collect data from a bar magnet falling through a conductive tube, to model this interaction computationally, and to compare and draw conclusions from both the observational and computational findings. Some background. Faraday's Law is one that discusses the change in magnetic flux and how that induces current and consequently magnetic fields. The Biot-Savart law is the equation that describes the magnetic field created by an electric current. The Lorentz force law, in our case, is where a magnet moving through a magnetic field will experience a magnetic force. And then we'll also be using Newton's second and third law to observe the situation. Prepping for the lab. As you can see, the large gray rectangle represents the aluminum foil, which will be the tube that we'll be dropping the magnet through. At the top, you'll see the bar magnet with a downward velocity as we drop it. And then to the right, you'll see a smartphone, which will be recording the process so that we can know how long the magnet was inside the tube. So some conceptual checkpoints. Why won't a ferrous tube like steel work for this experiment? If the tube was ferrous, like steel, that means it has iron in it. Iron is naturally magnetic, and if the tube were magnetic, the magnet would simply stick to the sides and it wouldn't actually fall through, so it wouldn't work. And secondly, how does this scenario compare to if the magnet were falling in free space? The only difference between this and that is that the magnet would fall freely and would only have a downward gravitational force, whereas in this case, there was also an upward magnetic force. So some of my data and findings. As you can see, the length, width, and radius of the tube are all at the top on the right. Using the magnetic dipole moment of the bar magnet from Lab 3, which was about 2, and then the mass of the magnet, which is about 0.023 kilograms, which we'll need to make some calculations later. But after doing 5 trials, I found an average time in tube to be 0.71 seconds. So let's see what the simulation said. So, firstly, what does the color indicate on the simulation? It represents the direction of the induced current as the magnet falls through the tube. So in this case, red represents counterclockwise if you're viewing it from above. And why is it red? That's because I dropped the magnet with the north pole facing downward. And so the change in magnetic flux was downward, and so by the Lenz's law, the induced current will create a magnetic field that opposes this change. So, what can be interpreted from the graph? The velocity versus time graph, as you can see here, shows an increase in magnitude of velocity, and then it kind of plateaus out and then continues to increase in magnitude. That long time in which velocity is the same will represent the terminal velocity, or how did the real world observation compare to the simulation? The simulation recorded about a 0.8 seconds to fall through the tube, and in the real world I got about 0.71. So I'd say that that's fairly accurate, and that the only differences between the two would be small factors such as air resistance. Maybe in the real world, the magnet hit the sides of the tube a little bit as it was falling through. And then in the simulation, to get a better view, we could have actually modeled even more rings. Modeled it perhaps as an integral instead of just summing them, because that would be a little bit more accurate. So some food for thought. What if the resistivity of the conductor were reduced as close as possible to 0? And how would the dynamics of the falling magnet change? Well, according to Ohm's law, if the resistivity of the conductor was reduced to as close to 0 as possible, then the induced current would be greater. And because the induced current is greater, the force on the magnet would also be greater. So the magnet would spend a longer time inside the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into the tube, the total time inside the tube of the magnet would decrease. because the magnetic force created by the rings will decrease. Conclusions. A magnet dropped through a non-ferrous conductive tube will experience an upward magnetic force and slow its motion, and this upward force will oppose that of gravity and cause the magnet to fall for longer than in free space. Thank you.